Welcome everybody to this session on human-AI collaboration for decision making. My name is Besmira Nushi and I am a researcher in the Adaptive Systems and Interaction Group here at Microsoft Research AI. Today I'll be co-chairing this session together with AJ Kamar, who is also a researcher in the same group. So the focus of this faculty summit has been the future of work, and of course AI technologies are starting to become important parts of our everyday work. However, we would like human-AI collaboration to become seamless and fluent. But as many of the people in the room here know, collaboration is not easy. This is not a modular process where you put the two parts together and hope that it will magically work. Instead, there are many aspects of collaboration that need to be planned and optimized carefully beforehand, either in the human and AI interaction or in the very foundation of the algorithms themselves. Today, we have an amazing line of speakers that have worked on collaboration in different aspects of it, either in the physical world or in human-AI decision-making, or from algorithmic transparency and interpretability. And the first speaker that I'd like to introduce is Ayanna Howard. Ayanna is a Linda and Mark Smith professor at Georgia Tech University and the chair of the School of Interactive Computing, where she leads the lab on human and automation systems. Her area of research is really centered around the concept of humanized intelligence, which in her own words is the process of embedding human cognitive capabilities into the control path of autonomous systems. Please welcome Ayanna.
Cool. All right, so what I'm going to do in this 25 minutes that I have with you is really introduce you into the world of experimentalists. And so I am an experimentalist. What that means is that I look at robotic systems, intelligent autonomous systems, so not necessarily Wizard of Oz systems, but real systems that have intelligence that interact with individuals in the real world. And when I say individuals, it's real people, not like labs and students, but it's actually individuals that you don't necessarily have a model of, and you try to. And so what I want to talk to you is really about the role of these systems when they're interacting with people, and the positive things that our systems can provide, also some of the concerns, as well as some of the bad that I see. And so I'd like to start off with the good, motivated by some of the work that I do. I look at, with respect to the good of this collaboration, I look at how do we use robots and AI technologies to engage children with special needs in therapy and educational opportunities. And so that's really the purvey of all of the things that I think about when designing systems. And so one of the nice things about working with kids is guarantee the kids are not your researchers. And so everything that we do and think about has to apply to this large demographic of individuals that we have to think about modeling and have this iteration with. And one of the things that I try to motivate people with at the start, even though there's a large demographic of children who have a disability, so 150 million children worldwide, we actually think this is understated, only because countries like the US, we're pretty good at reporting, but there are still some countries where it is not acceptable to have a child with a disability. So we actually think that that number is quite higher, but we'll go with the 150 million. And if you look at the world population, 15% of individuals currently are, if you look at all the census reports, have or live with a disability. And being in the accessibility world, we know this is larger. And so why I always motivate that as researchers, we should be thinking about this space is because we are designing technology that we might eventually have to use. And so if we live long enough, there is a stat that says if you live over the age of 70, which of course we all want to do, on average you'll live 8 years with a disability. And that could be a visual impairment, it could be a cognitive disability, it could be a motor disability, but it's some change in your normative function. It's something where robotics and AI technology could really engage and continue so that if you do live in the home, you have a quality of life. And so if you live in the home, and you can, with this augmentation with robotics and AI. And so I always put on my hat to say, as researchers, we should all be working in this space because we will eventually benefit from our own work. So that's just my little cap on that. And so if I look at children specifically, one of the nice things about robots is that it's a no-brainer. We don't have to come in and say, oh, can you interact with our systems? You know, these systems are going to help. It's more of a, what can it do? And there's also this over-expectation sometimes of what these systems can do. So it's actually a good problem to have. You don't have to try to convince your, say, customer segment to adopt your technology. It's already there. You bring a robot in, it's like, oh, what can it do? And I like to use it. The other thing about interacting and bringing robots is that we then have to make sure that when these robots are functioning, they are augmenting a human-human interaction. And so when we think about this interaction, especially since children are vulnerable, they are highly, they can be influenced, we have to make sure that when we design robots and we design AI technologies for this population, that it has to be based on human-human interaction. It can't be based on, well, the humans are doing it wrong, I think this is just a better thing, even though sometimes that might be the case. The fact is that we are influencing their behaviors. And so we have to really be careful when we introduce these AI systems that influence decision-making capabilities, that it still matches some type of normative function. It still maps to something that everyone else accepts. And so as researchers, we sometimes make decisions about what our AI systems can do. It may not necessarily be always optimal. It may not be necessarily efficient if you look at all of the metrics with respect to convergence and things like that, but it may be optimal with respect to the human. And so we are always very conscious of that, which also means that the system works. And so couple of the challenges that we have to deal with is that every individual is different. A lot of times as researchers, we think about, oh, there's like this baseline and there's this distribution and there's like this middle norm that everyone kind of falls and there's anomalies. But the fact is like everyone's an anomaly. And so when you think about technology, about designing technology such that every single individual is an anomaly, the decisions you make in terms of how your system adapts is much different versus we're going to design to this norm that we think about and everything else out to the extremes is anomaly. It's like, no, everyone is actually out to the extremes and the middle actually doesn't exist. And so they've shown some data that like that middle that we all love actually doesn't exist when you're interacting with people because people are different. Every individual has their different style. It might not be that time in the morning, maybe it changes in the evening and things like that. So that's one of the challenges is when we're designing these robots for doing therapy, for example, how are they moving? How can we model that? How can we figure out what they're doing in that moment in time? The other thing is that individuals, even adults, so if you remember the session that we heard in the morning about, our time, how our productivity goes down because of our emails and things like that. Some of that is focused on workload and switching context. We have really lost our ability necessarily to pay attention for a very long amount of time on one thing. For kids are actually designed, and the reason why is that they're wired to try to switch because they're learning about the world and the things that are going around them and cause and effects. And there's things that are so dynamic and changing so constantly that they're trying to bring this in. And so for kids, they are designed to actually do this switching, like, okay, I'm focusing on one thing, I'm focusing on another. Whereas adults, we actually learn how to focus and pay attention as us that are over the age of like 22, most of us. We have learned this. I will tell you for those faculty that are out there, the new generation, they're not designed and wired the same way in terms of paying attention. And so our robotic systems have to function in the domain where a kid is going to get bored very easily if the robot isn't engaging. A kid will turn off and not focus. And if a kid is not paying attention to the content, their learning outcomes decrease, their therapy and movement outcomes decrease. And so our goal with these AI systems is to ensure that we keep the child constantly engaged, changing our interaction, changing our behaviors so that we keep the child on task. And that's really understanding that they are designed not to stay on task, and therefore we have to engage them and maybe change the task to do that. And if we put that all together, we can create these systems. And so this is just a diagram of our entire AI system where we have gamified therapy, both tablet-based games as well as virtual reality games, where a child is doing things, everything from movement, trying to go across the midline, all the way to turn taking if I'm doing a behavioral therapy. And so we use the gamification to really engage the child. Of course, the therapists and clinicians need to know that it's working. They need to have the metrics. And so we establish all these metrics. And then if the robot is there to engage and keep the child on task, changing the task itself if necessary, or just engaging in terms of being socially interactive. And so when we put the system all together, we can show that our AI systems can influence behavior, can influence the decisions, can influence the movements of a child. And so our robots, I was classically trained as an engineer. I never really thought when I was going to school I'd have to understand things like cognitive science and neuroscience, but there are reasons why agents should have emotions. There's reasons why a chatbot that is socially engaging has better customer engagement. And it's because we as people, we are wired as social creatures. Our communication style has aspects of emotions in everything that we do. And so our robots, they mimic emotions in order to engage these kids. And what we can do is therefore we can show that over a time period, not only can the robots engage these children, keep them on task, but it influences their outcomes, whether it's behavioral, whether it's motor, whether it's educational at the end. And so we know, therefore, that AI can be used for this good and for this positive. And we have enough data that has been in the clinic as well as the home setting and not in the lab, because we do our testing out in the field, in the wild, to show that when we put these AI systems in the real world, that children do learn, children's behavior changes, and if we take and remove the agent, that some of those learning outcomes actually stay. So it's not necessarily, although if you look at our chart, it doesn't stay as much as we'd like, but there is some influence and there is some impact with the agent there even when we move. But one of the other things that we've also seen is that as we're designing these robots, because they're socially engaging, because they model these human-human interactions, we also see that children and adults are starting to trust and engage the decision-making abilities of these agents. And so this is a little bit of concern. So this is one study that we did where we had this engagement. We brought in these robots. They engage with individuals. And then we also looked at what is their interactions with the human therapist. And if you looked at the outcomes, the same, i.e. their learning of the task was the same, whether it was a human, whether it was an AI. But when we asked and probed about things like, well, what are your feelings about? What is your trust? What is your engagement? What we found is that with an agent, a robotic system, they trusted the agent better, even though outcomes were the same. So if you looked at what they learned, it was the same. But for the robot agent, there was an increased level of trust. There was an increased level of, yes, I would use that robotic platform. Again, I trust the decision-making capabilities of the robot platform, even though the human was the expert in this case, was the therapist, was the domain experts in this case. And so that started us thinking about this aspect of trust. And what does that mean? Because as you know, AI is not perfect. I mean, any system that's out there, even if it's 99.9%, there's that one chance where your system is failing. And if you think about decision-making capabilities and you're thinking about domains where you have high risk, that even if it's 1%, that could be of concern. If individuals are trusting the decision-making capabilities, then we have an issue. And so we started poking at that. And we couldn't do it in healthcare and kids, because remember, kids are highly influenced. And so if we introduce things like, well, what happens if the robot intentionally makes mistakes? We have a vulnerable population. That is not allowed. And so we thought about how can we evaluate this aspect of trust and over-trust when we have some AI systems. And so there's one scenario, and I'm going to talk about the bad, which is this aspect of trust. There's one scenario that everyone is trained in terms of behaviors, and what it is evacuation. So if the alarms went off right now, think about what would you do? you stand up, and if you're adults, you'd actually get up. If you're kids, you hold hands. You stand up and you look for your exit and you walk out. This is actually a behavior, it doesn't matter, you kind of learn, you get trained, you look for your exit signs. And so there's been studies, and what we wanted to see is what would happen if you had an agent that was introduced in the scenario, alarms went off, and there was an agent that was there and said, hey, let's come this way. And what we did is we intentionally did things like, if you're looking for your exit signs, we took the robot and put it in a place where it was counter to that. It was also counter to, there's some studies that have showed if there's no exit signs around, people, in terms of their navigation behavior, will go out the same way they came in. And so if there's no exit signs, it's like I came out that door, I came in, so I will go out. So that's the behavior. And so we wanted to see what would happen if you had an agent that would do that. So we invited participants to a building. They would come into the building, they would follow this robot, and we actually tried to remove this aspect of social interaction because we wanted, at least the physical in terms of being engaging, because we didn't want that to influence the behavior. So you would come in, you'd follow the robot to a room, you would go in. We had a big sign on the door because we didn't want them to know that the experiment was about to happen. And the big sign said, please close the door, sit down, read this article about robot navigation, and answer the survey questions like, a lot of HRI folks do. So they would close the door, they start reading. And as they were reading, what we did is we filled the building with smoke. And this is what you would see. So alarm goes off. What do? You stand up, you're like, oh, false alarm. You walk to the door, you open it up, and this is what they see. And so reactions are, some are, oh my gosh, there's smoke. Maybe it's not a false alarm. Let me find where the exit is. And so you kind of quickly move. And we, again, intentionally put the robot in a place that, you can see the exit sign, right? We intentionally put it where it wasn't the exit sign and it wasn't where you entered. And what we wanted to see is, first pass, what would you do? And if you followed the robot, you would actually go into this open area, which is not, again, outside. And what happened was we saw some very strange behaviors. Our first pass, where there was no mistakes, the AI agent just led you, it was 100% individuals would not go outside the door, would not go to the front door, they followed the robot. And so we said, well, maybe it's just because, they knew better or not, and so we kept pushing things in terms of mistakes and introducing. And what we found was that when you have these agents, and we poked a little bit afterwards in terms of interviews and surveys about what happened, but the kinds of behaviors we saw with this agent was actually, as a researcher, was baffling to ourselves, because we knew that there was this aspect of overtrust, but the level of overtrust was actually quite amazing. So things that we have, and you can kind of see some highlights, some was that individuals would literally stay with the robot. And so again, remember, the alarms are going off, there was smoke, you were just in this room, individual would stay. There was where we increased the risk, where there was clearly you couldn't see where the robot was leading to you. You had to physically do something. And so we thought, well, maybe because you're virtually walking, individuals would move furniture in order to go into these places. And again, it baffled us about these systems. And if you peel back a lot of the information about, well, why would you follow? Why would you do this? It made a mistake. What's going on? Some of it was, well, it's an intelligent system, and it must have information that I don't have. It must know something that I don't know. And the other thing was that, and it says emergency robot. So of course, it is an expert in this field, right? And we laugh at this, but this is the system that individuals are interacting with. I'm going to a customer service agent, I'm going to a chatbot, I'm going to a therapist that's online. It's a therapist, so it must know, even though my intuition says that something's wrong. And so this actually worries us as researchers. And so we're seeing this in a lot of our cases. We're now working with dementia patients, and this is something that and that's why I said it's bad, we as researchers in this domain, we really have to think about, as we're deploying these technologies, individuals are going to trust what they're doing, even though we're like, oh, but our accuracy is only 80%. That 20%, individuals are not necessarily going to feel and validate, be like, I think it's wrong, they're going to trust it. And so this is actually concerning. And then I want to go to, given that our AI agents might make mistakes and individuals are going to trust, kind of the ugly. And so there's been a lot of news about this aspect of ethics and AI and things like that. And we do know that systems are out there. And why I'm really concerned about that is that kind of a history is when we started in the space of interacting these robots with children, what we saw was in one of our studies, the outcomes were different for, I work with young kids, they were different for girls and boys. And you think like, why is that? Like, that makes no sense. And so as a researcher, you have to peel back and you're like, okay, there's some bump here, what's really this? And we were doing a study with children with autism. And the fact is more boys are diagnosed with autism. And so what happened was we looked and we like, oh, all of our learning data about behaviors and human-human interactions was based on clinicians interacting with boys. And so when we designed our entire system based on this, that was the data set. And in healthcare, again, children are influenced, and so we want the best kind of learning outcomes, the best kind of therapy outcomes for that. And so, and I always say, and I'm a girl, and this happened, right? And so this is something that we have to really be conscious of. And so we've looked at things like emotion recognition, because again, we have these socially interactive agents. We use a lot of emotions. One is recognizing children's emotions, as well as reciprocating. And as you know, most of the systems out there, of course, they're, kids. There's not a lot of kids data sets out there. If you go on the wild and do all the scraping, most times it's going to be adults. If you're older, there's also a bias, but definitely kids. So there's not a lot of data set that's out there for training. These things are out there. And one of the things we know with emotion recognition, if you have the data out there and you use people like Mechanical Turk workers to label it, there's different biases that we have. And they've done this and they've looked at this in the social scientists, where I'm more likely to recognize my own gender and my own race. And so if we think about the demographics of our workers, because I use Mechanical Turk as well, because they're there, it also means that our labeling is going to be representative of what's out there. And we know that there's biases. And of course, there's no Mechanical Turk workers, unless they're lying, that's like under the age of 12. And so of course, even the labeling of any kids' data sets that is out there is going to have some aspect of bias about, I don't know if that's a 5-year-old or a 10-year-old, I'll say 10. And that of course introduces errors into my system when I use that. And of course, like any good researcher, we kind of poke it. And so we've done a bunch of different analysis about what's out there currently, what's commercially available with respect to kids. And of course, there's a lot of happy and surprised kids out there, right? Like, imagine it, I'm a parent and I want to post something on YouTube. I'm not necessarily going to post my kid crying because I didn't give them that present. I'm going to post happy kids, right? Like, here's my kid and they're happy. And so most of these data sets, as well as most of the commercial applications that are out there, are really good at like happy kids. But if I'm in a therapy session, my kids are, I need to understand, and my robot needs to understand, if I have a child that's about to have a meltdown, there are expressions that are there that the robot needs to understand and know. I can't learn it if my data set doesn't represent that. And so we're trying to really fix that and dig that. And so we have some promising methodologies that are part of that. So some of it is training out the bias. How can we use what's already out there? Because we, as researchers, aren't going to create something that like the world is going to adopt. But is there a way that we can take what's already out there, what's out there in terms of APIs, commercially available, and put some type of filter, put some type of a lens on it so that you can still use whatever's out there, but put your lens. I have a kid's lens. Can I put a kid's lens on whatever's out there and still use it for my application and basically take out the bias? And so we've shown that with very little effort, we can basically remove bias based on our target demographic. So it's not this general, like, we're gonna remove all bias. It's I'm interested in an age bias, and therefore I can create a lens such that I can use commercially available systems that aren't trained on my age, on my kids, but I can then use it so that I can get the maximum benefit of that, but then have this isolation so it does work for my system. So we can definitely do that. And so I put the publication, as you know, and you put your publications up there so everyone can reference. And so the other thing is that I do have some hope. And so as we're looking at this aspect of bias and things like that, I think a lot of times as a roboticist, we do things like my robots, and there was no sound, but my robots, we use neutral voices, right? We actually don't necessarily use words, we use sounds, because we know that, again, because there's this bias with respect to definitely faces as well as voices. If I hear a certain type of voice, my interaction is going to be different. And so we also know that we can train this out. If we're conscious of these kind of things, we can do things differently. So we're thinking about decision making. I'm going to leave you though with this last study. We did one, and this is why I know this can work. If I show this type of robot, again, remember kids, and I say, you know, what's going on? Can you describe? Most individuals will say, oh, kind of range, oh, it's happy, it's dancing. Some might say it's a little agitated, I'm not sure, but kind of overall, it's a excited, surprise, you know, kind of thing. And if I just ask about a robot and emotions, that's the response I get. Now, as soon as a researcher, I do priming, which is I then define as, okay, this is a girl robot or this is a boy robot, or I give it a color, i.e., this is a black robot. What happens is people's perception changes. So without priming, people treat these agents as agents, like they have equal outcomes. But as soon as a researcher, I give it either a gender or an aspect of an age or a race, we get more comments of, it looks a little angry, I don't think I would want to interact with it. Again, if I take away this aspect of priming, I get the same outcomes. And so I think, again, as researchers, when we're designing these AI systems and we're deploying them out, so many times we actually will, my robots, I call them she, right? But I think what happens is when we label these things, all those human-human interaction biases come to the forefront of how we interact and how we will make our decisions and understand the decisions that are provided to us. And so I think as a researcher, we need to be a little bit more careful as we're deploying these systems about defining them with things that we know we have biases. And so my claim is like, we have biases. They're going to be in existence until probably all of us die, but it really is our role to not make our AI systems also inherit those, and there's certain things we can do by, like, for example, not calling them she's or he's or having some aspect of that. And so at the end, the takeaway is, I think, if you take nothing away from this, except that, you know, we overtrust emergency evacuation robots, is that as researchers, we do have a responsibility in this space. We have a responsibility of really consciously thinking about the things that we do for AI influencing individuals and making sure that we just don't do certain things. Because at the end of the day, you know, we're designing technology for people, right? And it's not necessarily we're designing it for our own students, we're designing it for individuals. And so focusing on that will allow us to really impact the world in a positive way. And so with that, I am done, and thank you.
We have a few minutes for questions. Please.
Hello, thank you. Yeah, question. I was wondering if you know about any correlations between the trust humans have to robots and the complexity of the robot.
So believe it or not, so we've done some studies with, like, they call it the cookie monster, like these blob monsters, blob robots that exhibit emotions through movement. And what we find is that those have more of a simulation of pets. The trust actually goes higher, but they don't see them as intelligent. So there's this aspect of, I trust it more, I think it's going to help me more, but I don't really think it's as intelligent. Whereas with a humanoid, it's a high trust and high intelligence.
Thank you. Great talk. I'm Savvy Savage from West Virginia University, and I'm also currently at Bing. How do you envision that we can start communicating maybe to end users the type of biases that certain robots or certain intelligent agents have? And is it important to communicate those biases that they might have?
I think it is, and why I say that. So we have a study where we actually just got accepted, where if a robot basically tells a user that it's uncertain, and we don't do like I'm 20% uncertain because we showed that that doesn't work. But if they say I'm a little bit uncertain about my representation, what happens is individuals will take the advice, but they won't take wrong advice. But that's being honest. So the robots are honest, and we show that the outcomes are still. And so we have this basically Simon Says task, and so they have to basically win the game. And when we provide information that says, I'm uncertain about this, but here's my answer, the outcomes end up being better, even when the robot is wrong. So yeah, being honest. I think we're good. We have 25 seconds. All right, so I want to thank you. And again, takeaways, everyone should be working on some aspect of accessibility. 2, we should really think about what we're doing as researchers and our impact on the world, and being conscious of our own biases when we're interacting with these decision-making agents. And with that, I'm down to 0. Thank you.
Thanks, Ayan. Please stand.
Our next speaker is John Kleinberg. John is an ACM fellow and is also a member of the National Academy of Sciences. And his research focuses at the interaction between networks and algorithms and their roles in our society. So it's my pleasure to welcome John Kleinberg.
Thanks very much. Okay, so in this session on humans and AI working together, I want to talk about some things that I've been looking at with a number of colleagues, and in particular my PhD student, Maithra Raghu, a number of colleagues at Google with Sendhil Mullainathan, a behavioral scientist, Ziad Obermeyer, an MD. And to think about not just the question of, on a given task, who's better at prediction, human or machine, but to think more broadly that the task of automation, broadly construed, is not the task of prediction on individual instances or the solution to individual instances, but rather it's the broader question of how to allocate effort within an entire workflow. And so we began thinking about a simple model of the allocation of effort as a broader optimization problem. And I want to start with that in a first domain. And then I want to move on to a second domain, in a way more of a toy domain, but one which is highly instrumented, where I think you can ask a lot of interesting questions. So the first domain, and this is sort of for concreteness to motivate the model, let's think about a canonical AI prediction problem like diagnosis from medical images. All right, so I see something obtained from a medical imaging system. In this case, it's a system to diagnose diabetic retinopathy that was developed in work with some of Maithra's colleagues at Google. It would like to estimate the severity of the diabetic retinopathy. And we often see this, and we immediately jump to the question, which is better, the human doctor or the algorithm? But we could think about the overall process by which this diagnosis takes place, and by which many diagnoses take place, and ask, given the performance of the human and the performance of the algorithm, and their performance characteristics, how should this task best be automated? Right? Which should be done by humans? Which should be done by machines? How does that work in a larger workflow? And we want to try thinking about a very simple model that would make that qualitative question concrete, so that we could think about it. And ideally, we could go back to this very same data and ultimately argue based on the model that the optimal performance is achieved neither through full automation nor through no use of algorithms, but through something in between. So how would that work? Well, for that to work, let's think about a kind of automation problem that someone in operations research or in optimization might think about in the absence of algorithms, right? So let's think we're in a kind of pre-algorithmic age. What we have is we have a set of n instances of some problem. And I'll just put up a small amount of notation here. It's not going to get much more notation than this. We have some small number of instances of a problem, n. Each one has a ground truth answer and some loss function that says how much cost is there to different kinds of errors. Now, I can allocate human effort to that task. And I have to decide how much effort do I allocate to each instance of the problem. And this is key to automation, that we don't tend to allocate effort uniformly across all of the tasks that we face. Even in this medical context, right? Concepts like seeking a second opinion, assigning a second or third person to this particular case, revisiting this case because it seems particularly tricky. All of these are ways in which we non-uniformly allocate effort. And what we'll argue is that that's actually key to how we might think about the role of algorithms as well. So continuing with our notation here, let's imagine that if I assign k units of human effort to task x, I'll get an answer h of xk, and that incurs a loss f of xk. Okay. Now, it's important that for two different instances of the problem, x and x prime, they might have very different functional forms as a function of effort. Some tasks might be easy, and so the first unit of effort does a lot of good, and the other ones have very low marginal gain. Some might be hard and reward increased effort, so the loss just keeps going down, down, down as I assign effort. Some might be hard but not benefit from extra effort. It's just going to be hard no matter how many people you assign to it. So with that in mind, I'd like to effectively, again, in the absence of any algorithms, solve the following optimization problem. For each instance x, assign kx units of effort to do two things. Respect the budget of effort I have. I have a total effort budget of b. And two, minimize the total loss, right? So I'd like to minimize the sum of these f functions, the total loss, subject to the sum of all my effort allocations adding up to most b. All right. What happens when we add algorithms to the picture? Now we have an additional choice, but let's stay within the same kind of workflow. Right? So the algorithm can also provide an answer, let's call it m of x, and incur a loss, let's call it g of x. So now I'm not just trying to decide how to allocate the human effort. I'm also trying to decide which subset of the instances do I fully automate so that the human never even sees it. Right? It's a form of algorithm as triage, in which there's a set S that only the algorithm works on, and then the humans work on the other instances, possibly assisted by the algorithm, but that's in a sense implicit in the model. And so now my new optimization problem is the minimization is now over a sum of two terms. The first term is the loss incurred by the parts I fully automate. And the second term is the loss on the parts that I allocate human effort to. Again, respecting the budget. OK. So again, just to recap, that's what's going on here. First of all, this suggests a few things. One, it suggests that we don't just need, when we're thinking about automation with algorithms, an algorithmic prediction, right? We can't just say, let's work as hard as we can on getting m of x. We need to estimate two other quantities in order to make sense of this optimization problem, this allocation of effort. One is we need a good estimate of g of x, the loss incurred by the algorithm. Right? The algorithm needs a good assessment of its own likelihood of error on a per instance basis. It needs to know it's doing well on some instances, worse on others. Second, we need to be able to aim the algorithm at the human and assess human error, right? Because we need estimates of these functions f of x comma k. The algorithm needs to understand, to guide the optimization problem, what is the return to assigning k units of effort on this task x. Right? So all three of these things, good algorithmic predictions, good self-assessment of its own error by the algorithm, and good assessment of human error, all naturally show up if we're going to optimally allocate these things. Why do we expect that the correct answer might not be full automation or no automation? Well, because if I think about the balancing of those two terms, then something which might be going on here is that, first of all, by automating, I free up human effort that I can then double up on certain problems that the algorithm is working with the human on, right? So maybe rather than having one person on each instance, I have two people on some of the instances or three people. That effort has been freed up by automating some of them. And secondly, the algorithm may actually be able to detect that some instances are genuinely better for the human, right? There may be some that the human will do better at, and maybe the algorithm can recognize that. So we tried some simple heuristics here, going back to this diabetic retinopathy data set, where these most recent trials that have been done suggest that algorithms are comparable to, or in fact outperform, human doctors. And essentially, without going into many of the details, we can sort all the instances by the algorithm's predicted gain, right? How much better will it do than the human? And it simply triages them in that order, right? If I would like to automate an alpha fraction of all the instances, then I sort all the instances by the gain from using the algorithm instead of the human. I automate the first alpha fraction, and then I optimally assign the effort of humans on the rest. What happens when we try that? Well, I have two plots here that sort of suggest the two things that we thought might happen in fact happen here. On the left is a histogram showing the algorithm's estimate of the expected human error minus algorithmic error. So on the right-hand side, you see these blue bars in the histogram. That's the positive part of the axis. That's where the algorithm expects that it is outperforming the human. maybe more interestingly, on the left, you see these orange bars. That is where the algorithm expects that actually the human is going to outperform it on these instances where it's making predictions, right? The orange bars are lower, reflecting the genuine fact that the algorithm is actually making lower error rates than the humans. But both sides of the histogram are populated, meaning there is actually gains to partitioning these instances correctly across places where the algorithm is doing better or where the human is doing better. And secondly, we free up human effort to double up on certain of these things. So on the right-hand panel, we have plots of the total aggregate error under different proportions of cases that we automate, right? So over there on the right, if we automate everything, we have the performance of a very simple workflow, just full automation of all instances. Over on the left is another simple workflow, which is we simply don't automate anything and we just assign human effort. And in between, we have an interior minimum on the error. If we automate some but not all, then with the residual human effort and with the algorithm's ability to recognize the cases where the humans are going to provide the most value in the process, we actually get an error rate that's lower than either extreme. Right? So with optimal triage, neither full automation nor pure human effort turns out to be the optimal way to solve this optimization problem. Even on these very well-studied data sets where in aggregate algorithmic performance is higher. And we see that as kind of striking because often, a sort of cursory gloss on some of these situations is to say the algorithm has now exceeded human performance. Let's start thinking about the implications for full automation. But the point at which algorithm exceeds human performance is not necessarily some sort of a discontinuity. It's not necessarily some kind of a sharp break with the status quo. It's rather simply a point in a continuously morphing system in which we want to be offloading more and more onto the algorithm, but still preserving some amount of human effort to achieve optimal performance. So that was one thing that we looked at in this very concrete domain where we could look at heterogeneity and the difficulty of instances and how we automate. But there are many richer questions that we can ask. And for those, we began moving to other domains, which, as you will see, are less consequential than medical diagnosis, but which are really beautifully instrumented and become fascinating model systems in which to ask these questions. So in particular, here's a question that I'd like to layer into all of this. So far, we've thought about the instances as varied and heterogeneous, but we've thought of the human beings as essentially interchangeable. All the humans are assumed to have the average skill level, the average ability to diagnose. But of course, in the same way that problem instances are heterogeneous, human experts are also heterogeneous in their abilities, in differential comfort level with different kinds of situations, and so forth. So we can sort of think of the skill difficulty plane, right? If I want to think about the probability of error on a given instance by a given expert, right? Along one axis is the skill of the person performing the task. And on the other axis is the difficulty of the instance. And the question is, how does the probability of error depend on these two things? And you can sort of notionally imagine that that error surface, could look like the one on the left, which has a sharp tilt in the skill direction, right? It really rewards gains to skill, and a very gradual slope in difficulty, right? Increased difficulty doesn't really affect performance, but increased skill has huge payoffs. Or maybe the error surface is tilted like in the other panel, right? Sharply from front to back, which means it's a kind of problem where small differences in difficulty cause huge effects on error, whereas skill is sort of a second-order term. And for any given domain, we ought to be asking the question, what kind of surface are we on? If I'm trying to figure out how do I reduce error, is it more critical these fine-grained differences in difficulty, or are differences in skill? How could we study this? We would need a domain that's highly instrumented, where we have all of this kind of information, where humans, through a lot of study, have achieved some form of mastery, and yet where, despite that, computers are that much better still, so we can actually look and analyze even the best humans and try to figure out where they're doing well and where they're doing poorly. Okay, so we found such a domain, right? A domain where a century of human scholarly activity has essentially been eviscerated by computers to the point where humans effectively have nothing left to offer, and that's chess. Okay, so chess is something with an incredible amount of skill being deployed, but where sometime around 2005, the 2005 to 2007 era truly was a kind of singularity in chess, in the sense that the last time a human chess player in a recorded tournament game beat a computer was roughly 2005. Okay, computers are now so the era of Kasparov and Deep Blue fighting it out in equal terms is truly 20 years ago. If you pair up the best human and the best computer and ask them to play as a team, we're even at a point now where the best thing the human can do is just listen to the computer and do what it says. Okay? Now, chess has long been a model system, right? It's one of the few things to have been called metaphorically the Drosophila of two different domains. John McCarthy called it the Drosophila of AI. Simon and Chase famously called it the Drosophila of psychology. Perhaps they should have said cognitive psychology. But it's because it really provides us with data on a sequence of cognitively difficult tasks where we know the skill of the player, we know the instance itself, we can try to assess its difficulty. We have things like the time available to make the decision. And so the question is, can we use this to analyze human performance along the dimensions, right, in this kind of skilled difficulty plane, given how highly instrumented this is? Right, so this is a typical instance that we'd be looking at, two chess players. On the right is actually Magnus Carlsen, a 28-year-old Norwegian chess player who's believed to be the best person ever to play chess in human history. And we're going to use the algorithm to try to characterize what are called human blunders, right, in chess parlance. Okay, now, despite the fact that computers are extremely good, there is the problem that in the end, they're not playing chess perfectly. And so when a computer says that a human has made a suboptimal move in a given situation, in the end, maybe that's the computer's suboptimality. Maybe it's almost a question of taste in a sense, which move was better. So we wanted a place where we could really diagnose actual mistakes. How do we do that? And so what we did was took advantage of another development in computer chess, not the ones that we tend to see in which chess engines have become so strong, but rather a more technical one, that for positions with at most 7 pieces on the board, chess has in fact been solved. Right? There's a bounded number of ways you can arrange 7 pieces on a chessboard. It's very large, but with a few terabytes of storage, you can now play that part of chess by table lookup. Right? All positions are now equally easy or hard for the computer. It just looks up what to do because it's pre-computed absolutely everything. Okay? And so that frame I took from a YouTube video of Magnus Carlsen playing Peter's Fiddler from Russia. If you play it forward another minute or two and you read the YouTube comments where people are following along what's going on, you get to this point in the game, 5 pieces left on the board. Magnus's hand is poised over the rook, and you plug it into your table base to see what should happen. There are 18 legal moves for white. 9 of them win at various depths, and 9 of them draw. Okay? Exactly half the moves win. And if you play it forward a few more seconds, you see that Magnus grabs the rook, pulls it back 1 square to the square g2. And you look that up in the right-hand column, rook from g3 to g2, draw. Right? Magnus, the best player ever to play chess in human history, has just thrown away the win, and it is now a draw in a 5-piece chess endgame. Right? These situations are cognitively difficult even for the best people in the world. And there's an enormous amount of data. Right? So with Ashton Anderson and Senthil Mullainathan, we went to the free internet chess server, where people, amateurs, not Magnus Carlsen necessarily, but amateurs play online. 200 million recorded games, right, with the exact moves, the skill ratings of each player via their chess rating, the amount of time taken, all of these things. Okay? And we took all instances with at most 6 pieces because we wanted to sort of not be at the outer limit of what was feasible. And we asked, did this move change the win-loss draw outcome of the game, in which case we'll classify it in chess parlance as a blunder. Okay? And so we can ask, how does this depend on skill? How does it depend on difficulty? Right? These 2 axes that we wanted to think about. Okay, skill. We can do a simple sanity check. So in chess, players have something called a rating, the ELO system of ratings, which is, by all agreements, a relatively good one-dimensional heuristic rating that's also been applied in other sports. And on the free internet chess server, the ratings, just for calibration, range roughly between 1,000 and 2,000. 2,000 is quite a strong amateur. 1,000 is sort of an elementary school class champion. And we also took a smaller amount of data from actual world-class games where the ratings run, say, from 2,300 to 2,700. There are about 50 people in the world rated 2,700. And we see, as you would hope, that the rate of blunders is going down smoothly, monotonically. And obviously, the y-axis in the right-hand panel is much smaller than the y-axis on the left because these are incredibly good players. How about difficulty? That, of course, is an interesting challenge itself. How would you quantify the difficulty of a position? There's much that could be done here. And after trying a number of things, we actually, for the purposes of this analysis, settled on something that is simple, but we don't have a much better substitute readily at hand. We'll call it the blunder potential. What is the probability of blundering, namely changing the min-max value of the game, changing the win-loss draw outcome, if you were to move at random? Right? So in that position from before where Magnus blundered, there were 18 legal moves. 9 of them preserved the win, and 9 of them threw it away. So that's a blunder potential of 9/18, or actually exactly 1/2. Okay? And what we find is that if you plot this, look at this heat map on the right, as the blunder potential in position goes up, the probability that you make a blunder also monotonically goes up, which makes sense, although in fact some intuition from things like complexity theory tells us that the hardest instances of a problem are generally not the ones with a unique solution. So you might have imagined that the things with the highest blunder potential, the answer of what to do would be self-evident. If there's only one thing you can do, you might see it. Surely that is true in certain cases, but on average, that is not the case. On average, the blunder rate just goes up monotonically with the probability of random blunders. Okay, so we have these 2 dimensions. Well, with that in mind, we could try to formulate a prediction problem, right? Let's move into the skill difficulty plane and ask, what does the error surface look like? Is it tilted toward skill, or is it tilted toward difficulty? So we tried a number of variations on this. One, which threw in a bunch of other features as well, was to say, let's consider this as a prediction problem. Given an instance of the problem, right? That photo is an instance of the problem, right? The position on the board. We'll also record the rating of the player making the move, the rating of the opponent, in case that matters, the time remaining, in case that matters, the blunder potential, that's our measure of difficulty, and a set of other heuristic attempts at capturing difficulty. Okay? We took all of those, and we did some standard off-the-shelf machine learning on this relatively low-dimensional problem, just to see which features were going to be the most informative. And we found something interesting, that the algorithm came away with a strong opinion on which way the error surface was tilted in the skill difficulty plane. Because if we used all features, we created an artificially balanced data set in which half of the instances were blunders and half weren't. If they used all features, they got 75% accuracy on this balanced data set. If they used only blunder potential, right, this one-dimensional feature, that what is the probability you make a mistake if you move at random, you got 73% accuracy. Right? Almost all the gains to prediction were in that single number. Whereas if we looked at the rating of the player and of their opponent, you got 54% accuracy. Right? So to the algorithm, looking at the error surface, it effectively is saying, this thing you call blunder potential that you're using as proxy for difficulty, that's everything. It's fundamentally that. And if you look at this thing you call skill, about which many books have been written, well, what is the basis of chess skill? That's a low-order term in this prediction problem. And we go back to the data and we realize it's actually, you can sort of see that. So remember, this is the dependence on skill. Let me stratify it by the blunder potential. Right? So the blunder potential could be 0.1 or 0.2 or 0.3. Right? Positions get harder and harder. Let's look at this curve, but only over subsets of constant blunder potential. And here they are. And this is kind of a visualization in a sense of that metaphorical plane that I had drawn earlier. What you see is, say in the left-hand panel, these downward sloping curves. The top one is for blunder potential 0.9. The next one is for 0.8. Next one's for 0.7. So harder categories of positions are higher up, higher rate of blunders. That makes sense. But notice how shallow those curves are compared to how much gap there is between them. Right? So players rated 1800 faced with a position of blunder potential 0.9 are doing worse than players rated 1200, these elementary school class champions, on positions of blunder potential 0.8. And at 0.8, these really good players are doing worse than the really weak players at 0.7. And you just keep going down. Right? An extra 0.1 in blunder potential is leading to a higher rate of error than 600 rating points, which is an enormous difference between chess players. In a way, it's even more extreme. If I go over to the right-hand panel and I read the y-axis, I discover that players rated 2700, remember there are 50 of them in the world, in a position of blunder potential 0.8, are making blunders at a rate of about 0.045, right? About a 4% rate. I go back to the left-hand panel. I look at positions of blunder potential 0.2, relatively easy ones. Players rated 1200 are making errors at a rate of about 0.03, right? Less. Right? So you would, if your life depended on someone not making an error, you would rather have the elementary school player in a position of 0.2, difficulty 0.2, than one of the top 50 players in the world in a position of difficulty 0.8. Again, on randomly drawn positions. Every position has its own idiosyncrasies. Now, this was surprising to us. But the fact that it's surprising to us is actually its own field of study, right? It's known in psychology as the fundamental attribution error. the tendency to impute outcomes and situations to the individual taking the action and not to the context in which they're acting, right? You see somebody make a mistake, mess something up, and you say, boy, they must not be very good, and you tend not to think as much, they must have been in a very difficult situation where the task was very challenging. And that's exactly, in a sense, our surprise is a reflection of that, right? The difficulty is really dominant here. This is not to say the higher rated players don't win chess games, because chess games are not decided by the outcome of one move, right? It's an accumulation of small advantages over 40 moves or 60 moves. The better player in aggregate is winning in that biased walk. But position by position, difficulty is an enormous factor. I just wanted to show you a few snapshots of other things, because we do think this is an incredibly rich data set to get into some of the aspects of human skill, difficulty, the nature of error. You could, for example, fix the exact position, right? So with 200 million games, you can go into the simplest positions, and they have occurred literally thousands of times in the data verbatim. So I could fix an exact position P. I could say, let's say F sub P of R is the blunder rate in that exact position for a player of rating R. Right? So you'd expect that the blunder rate would, again, slope downward as the rating goes up. And for most positions, that's true. But you get some strange positions, right? So the one on the left is what you'd expect. It says, in this exact position, better players are making fewer errors. The one on the right, it goes up. Right? This is what we call a skill anomalous position. We hadn't expected they would necessarily exist in the data, but it's one where better players are actually making more mistakes. Right? And the chessboard is symmetric left to right. The chessboard is symmetric between black pieces and white pieces. If you try all 4 symmetric versions of that position, they all slope up. Right? There's something really robust in that position. A number of other things. We could put it all into a scatter plot. It's amazing how many orders of magnitude difficulty spans in this domain, right? Ranging from positions where only 1 in 200 people make a mistake to positions where only 1 in 200 people get it correctly, right? It's a way to sort of automatically discover the very hard instances from the data. In some of these instances, and this will be the point on which I leave before wrapping up, there are a number of theories as to what's going on here, and it's going to surely be a composite of many of them. But one interesting one that we've been seeing in a number of cases is blunders arising from what you might call misleading analogies. So the position in the upper left, just a king and a pawn versus a king, has a blunder rate of 0.755 in the several hundred times it's occurred. Okay? And the correct move is to drop the king straight back, not drop it back diagonally. But if I translate that position anywhere else on the board, the correct thing to do flips. The correct thing is to drop it back diagonally, not straight back. And those positions all have much lower blunder rate. Right? So this is just one indication of some of the kinds of challenges that people face as they apply problem-solving heuristics to this. So a number of reflections. Surely it can't be that difficulty is the only thing here. More broadly, do we have a more systematic way of trying to induce knowledge of human heuristics and blind spots from this incredibly rich source of data? But to come all the way back to this top-level point, in the end, automation via algorithms is not really just going to be some sort of horse race between algorithmic performance and human performance. And I think the talks yesterday and today contain many illustrations of that point. It's going to involve thinking about the workflow, the allocation of human effort. And I think a core component of that is going to be to think about what makes individual instances easy or difficult, and how do they respond to greater or lesser amounts of human skill as we think about humans and AI collectively working on solving these problems. Thanks very much.
We have time for some questions.
Thank you. Nice talk, John. 2 quick questions. First, there's also this aspect of learning of humans. You want to pose them problems so that eventually they will become better players or better task doers. So what's your sense? I mean, you have to optimize the system at the much longer term horizon than just trying to solve a specific sequence.
Yeah, it's a nice question, right? So how do we present instances to people in any domain, right? In chess, in medicine, in law, that are going to somehow are going to help people improve? I think in what we saw in chess, it was actually quite thought-provoking. Right, this third bullet, implications of empirical blunder data for teaching, that if we think about the canonical way to teach something like chess endgame play, you would give someone a book and it taxonomizes, here's king and pawn versus king endings, here's with bishops, here's with rooks, and so forth. And it's sort of, you engage in introspection and you taxonomize the space. It feels like when you look at the rate at which people make blunders and the vast swaths of easy positions, that with that kind of data, you could easily say, let's spend time on this kind of instance because it's very hard. Whereas this instance we'll treat very lightly because when you get to it, you'll know what to do. We know that from the data. And so I think that also can sort of help us in the allocation of effort, what instances to expose people to. And I think there are a lot of interesting open questions here.
Yeah, and just a follow-up. There are also these tasks that involve there be multiple agents, humans and agents
Yes.
that are working together. So you cannot allocate one fraction, one task to one person. It's a team. And
Yes.
what's your thinking about how do we look at that kind of problems that you cannot just divide to one agent?
Right. No, I think that's interesting. And actually, in the medical data, there's an interesting question about aggregation, obviously, and many people are giving thought to this, that if we say we've freed up human effort so we can now have multiple people look at this, we could have multiple people look independently and do some kind of aggregation in an arithmetic sense. We could have people look collaboratively. If an algorithm is providing input into that process, what's the best way they can contribute depending on how the team is combining its input are all very interesting questions.
Hello, John, just a clarification question. In the chess, when the expert player lose a game, do they get a rapid decline in the rating? I was wondering whether that has to do with the way they behave. And in the deception literature, they say the same thing. When the stakes are high, you leak out a lot more information when the stakes are neutral.
Yeah, right. So in general, with the online games, and actually my co-author Ashley Anderson has done some very interesting work on how people respond to the possibility of gaining rating points or losing rating points. You should think of the ELO rating system, which actually was a very nice probabilistic generalization, was done at Microsoft Research through the True Skill system, which is used in Microsoft Online games. It's essentially a kind of probabilistic learning process to try figuring out the person's true ability. So if I beat someone who's stronger than me, I gain a lot of rating points and they lose points. If I beat someone weaker than me, I gain a few and they lose a few, and so forth. So each individual game has less impact on the rating than the sort of accumulation of a long session of games. And one thing Ashton has looked at is people's behavior over the course of a long session as they stake more or fewer points. Of course, in the data we have on professionals playing tournaments, each game is obviously treated extremely seriously, and the stakes are correspondingly higher.
Okay, thank you, John. We'll move on to our next speaker.
Thanks very much.
Our last speaker for the session is Rich Caruana. Rich is a principal researcher at MSRAI, and he has been doing a lot of work on machine learning, multitask learning, model compression, and more recently on interpretability and explainability for healthcare problems.
Great. So thanks for being here, and thanks for inviting me to speak. So I'm going to talk about the ways in which interpretable machine learning, transparent machine learning, can sort of help turn us into detectives, good data scientists. So that's where we're going to go. Let me start first with acknowledging many of my co-authors who have worked on this the last 7 years. Some of these are interns and grad students. Some of them are collaborators here at Microsoft, and others are MDs at hospitals and other people at other universities. So I won't name everybody. Some of them are in the room here, though. So let me start with a quote from Sherlock Holmes. This is the Hound of the Baskervilles. Sherlock Holmes says to Dr. Mortimer when he's meeting them, "You saw footprints?" And Mortimer says, "Yes, footprints." And Holmes says, "A man's or a woman's footprints?" To which Mortimer pauses and replies, "Mr. Holmes, they were the footprints of a gigantic hound." So what we're going to talk about is footprints, detection, following the clues, and the relationship to data science. And the surprises that can happen, right? It wasn't a man's or a woman's footprints. It turned out to be a hound. In this case, a glowing hound. Okay, so as data scientists or detectives, of course, the tools that we use are very important. Now, as many of you may know, there tends to be this trade-off in machine learning where the most accurate models, models in the upper left here, things like boosted trees, deep neural nets, random forests, tend, unfortunately, to not be very interpretable. So they're going to make it harder for us to be good detectives because we're not going to be able to understand what they're doing. And then models in the bottom right of this plot, things like small decision trees, logistic linear regression, they're very nice and interpretable. They're easy for us to understand. Unfortunately, they're just not so accurate on a lot of problems. So we'd really love to stick with the more accurate models in the upper left-hand corner here. Unfortunately, those things are, as I said, black boxes. We can't really understand what they're doing. And what we would love to do is somehow maintain that accuracy, but move that black box to being some sort of white box in the upper right-hand corner of this space. And an interesting question arises, do any methods actually exist that can have a combination of high accuracy and high interpretability? It's possible that it's actually just theoretically impossible in general. We've had some success over the last 7-8 years of putting one algorithm up there. It's not ideal for all data sets, but for many data sets, this is extremely competitive and it's very interpretable. And we've called this generalized additive models with pairwise interactions, and I'll tell you about that. By the way, for those of you who saw the presentation I gave yesterday, there will only be overlap in the very beginning of this presentation, and then we'll get on to new stuff. So I don't want to bore you with the same things a second time. So let's talk about the space of model complexity. At the top, we have very simple models. It's a function time, a weight times a feature plus a weight times a feature, beta times x1 plus beta 2 times x2. That's linear regression. And then down at the bottom, we have full complexity models. So these are things which are just an arbitrarily complex function of all the features at the same time. Fortunately, there's something in between, and this is the space of what's known as additive models, where we have a function of a feature plus another function of another feature. These are all functions of single features at a time. That's very important. And then they're combined with addition. That's also important. And this is a very restricted model space. And fortunately, it's going to turn out that if done well, you can get pretty good accuracy out of this. And it's going to remain very intelligible. So now we can make that a little more complex. The first sum over I is the sum of all functions of individual features. That's what I showed on the previous line. But then we can have the sum over all ij for functions of pairs of features, and now we can have pairwise interactions in the model. That makes it a little less restricted and now more accurate. And we can go to three-way combinations of features and do three-way interactions. If we go far enough, though, we get back to a full complexity model that we can no longer understand. And in fact, what we're going to do is restrict ourselves to just functions of main effects. Okay, so that's functions of individual features, plus a small number of functions of pairwise interactions, just the ones that are most important. Now, we didn't invent these. They were invented by statisticians down at Stanford in the late 80s. So these have been around a long time and, in fact, predate much of machine learning. Rob Tibshirani and Trevor Hastie are the ones who invented these. However, they were a little overly conservative, the way statisticians tend to be, when they fit these models. And because of that, they tended to fit them with very low complexity, smooth functions. And that means they didn't get very high accuracy out of them. And surprisingly, it also means they didn't get high intelligibility or interpretability out of them. So our contribution to the GAMS world is going to be to fit these with modern machine learning techniques, and in the process get very high accuracy out of them, accuracy that, in fact, most of us thought was not possible. And surprisingly, we're also going to get very good intelligibility out of them by improving their accuracy. So now I'm going to skip the technical details of the algorithm. I'd much rather show you the kinds of things that this class of models can help us do when we're trying to do good data science detective work. So this is a data set from the late 80s. It's a pneumonia data set. I'm just going to use it to illustrate a few things, and then we'll go on to some other data sets. There's 46 features in this data set, and the model class is a function of a feature plus a function of a feature. So there's going to be 46 functions. And then we'll throw in 10 pairwise interactions. So there'll be 56 functions altogether. And all of these are learned at the same time with a complex algorithm. But I'll spare you the details of that. So here's what some of these features look like. So each feature, each main effect, is essentially a graph. So we have a function of age, a function of asthma, a function of your blood urea nitrogen, things like that. And the way you use these functions is you find your age in the graph, you read across the x-axis, you find your age, you find where the y value is for that age, and you write down that y value. And maybe it's minus 0.23 for you or for some patient. And the way it works is negative numbers lower your risk. These are log odds. And positive numbers increase your risk. So you want to be as negative as you can be, because that means your chance of dying from pneumonia in this case is minimized. So what we do is we add up all of those numbers, and that gives us a score for the patient. Remember, there's 56 graphs in this model. So we get 56 numbers. We add them all up. The more negative that sum is, the lower the risk. The more positive the sum, the higher risk. And then we just do 1 over 1 plus e to the minus score to convert this to, in this case, we're predicting probability of death. So maybe the score that we got for this patient when we added all the numbers up was minus 0.78. That's actually a pretty large log odds. You'd rather be a minus 3 or a minus 4. But if you calculate a probability out of that, you get about a 30% chance of dying, which is a very high probability of death. So you don't want to be a patient who has this high of a score. So now let me show you, let's zoom in on risk as a function of age. So this is just one of the 56 graphs. On the bottom, we have a histogram of the patient population that we're seeing. Most patients are between 60 and 90. Had to be an adult to be in the data set, so everybody's over 18. And the top graph is what the model has learned about risk, your chance of dying, your log odds of dying as a function of your age. So let's quickly interpret that graph. So down is low risk. So the left side of the graph is the low risk side of the graph. That's for young people. And youth seems to end at about 50. So everybody under 50 is treated as being equally low risk and young. Okay? So it doesn't seem to distinguish between people in their 20s, 30s, and 40s, even though it could. Then risk is going up slowly as you go through your 50s and into your 60s. And then there's a sudden rise in risk that's happening around 67, 68. Now, risk is going up pretty rapidly as you go through your 70s and into your 80s. There's a surprising step function increase in risk right at 85, which is a very round number, so it's interesting. And then the risk is kind of flat as you go through your late 80s and through your 90s. And then there's an even more surprising drop in risk that's happening right at around 100, 101. So let's just talk about a few of these features in the graph. The rise in risk at 67, 68, that's almost certainly due to retirement. So this is a data set from 1989. Many people would have retired at about that age or just before that age. You might have thought retirement was good for you. If you've got pneumonia, apparently retirement can be bad for you. Many possible explanations for that. Maybe your daily activity has changed. Your urgency to get to care has changed. Your insurance provider may have changed. Your doctor may have changed. You might have moved and not even have a doctor where you've moved to. Who knows why? But somehow in the aggregate, all these factors associated with retirement for the average person have a net decrease in chance of survival as opposed to an improvement in chance of survival. So your risk goes up. Now this rise at 85, that's really a surprise. There's nothing in healthcare policy or insurance policy that says we should treat 86-year-olds different than 84-year-olds. And yet the model's actually pretty sure that this is happening. We've talked to doctors, and what doctors have told us is that, well, back in 89, being over 85 really puts you on the sort of elderly side of old. In fact, a lot of medical data sets back then didn't even record how old you were over 85. They just checked the sort of 85 plus box. And we think it's in effect kind of like this. Grandpa's 86 years old. Grandpa's very elderly, has a number of comorbidities associated with being elderly. Because of that, Grandpa's now got pneumonia. He's very sick. First round of antibiotics hasn't really worked. Perhaps we should let Grandpa pass. Like maybe that would be the friendlier thing to do for Grandpa. His time is coming soon anyway. Maybe we should let it happen now. And there was even a phrase that was used for pneumonia back in the 80s and earlier, which was pneumonia is the old man's best friend. This idea that it was maybe a kinder, gentler way for a person to pass than a sort of long, wasting illness. So anyway, that's our explanation for what's happening at 85. When we see these step function things at round numbers, it's often that sort of thing. This flatness through the 90s was also a surprise. We think that might be a sign of what's known as successful agers, people who have taken pretty good care of themselves physically. They have good genes. And if they've made it this far, maybe at 95, they're not actually at any higher risk of dying from pneumonia than they were at 90. So maybe that's what the flatness is due to, although we're not sure about that. The drop at 100, that's the biggest surprise, right? So 100 is another very round number, and it's a very important round number for humans. You become a centenarian. And centenarians back in '89, when this data was collected, are pretty rare things. So we think what's happening is the opposite of what's happening at 85, where we're giving a little less aggressive treatment to somebody who's crossed the threshold of 85. We think now if you've crossed the threshold of being over 100, you're a centenarian, we're actually giving you even more aggressive treatment. As in, pneumonia is a very treatable illness. You've made it this far. You've made it to 100. We're just not going to let pneumonia be the thing that takes you out. If you need that third round of antibiotics, we're going to give it to you. We're going for the record. We're going to get you by this as best we can so that you've got another year, perhaps. So we think that's, again, a social effect. OK, we've just spent some time telling some stories about one of the 56 graphs that's in this model. Well, one thing that's interesting is that these graphs are the model. This is not some approximation of some other more complex model. This really is the model. Now, the stories, of course, are things that we're looking at the model, and then we're the ones who are trying to play detective and figure out what the model's doing, why the model is doing what it's doing. But we know exactly how the model is going to make its predictions because we can see these graphs. The model, it turns out, it's the most accurate model we can train. It's more accurate than any other model anyone has ever trained on this data set. So it turns out there's no loss in using a model that's this intelligible for this kind of problem. So you might as well use a model where you can actually understand everything, as opposed to, say, some black box model like a random forest or a neural net, where you wouldn't understand these sorts of things that are happening in the model. Moreover, because the model is these graphs, we can actually edit the model. So I mean, how many people think that a person who's 105 is actually intrinsically lower risk than a person who's not 95, right? That doesn't make sense biologically. So one of the things we can do is we can modify the model. We can redraw that part of the model, make risk go slowly monotonically up, perhaps past age 80 or 85. And if we do that, the model will do our bidding. Now, we got to be careful. We're overruling the statistics in the data. The statistics in the data really do suggest that people over 100 are lower risk, but we don't think it's because they're intrinsically biologically lower risk. We think it's because they've received exceptional care once they break this magic threshold of 100. So we've got to decide whether this is appropriate or not for us to overrule the statistics. Now, there are other things we could do. We could maybe fix this jump that happens at 85, but I'm actually happy to leave that in the model because that, our explanation for that is that the patients over 85 aren't getting as aggressive treatment as the patients under 85. So if I predict that they're higher risk, then maybe they'll get more aggressive treatment. So this could only be good for the patients, is what we're thinking by leaving that in the model. And then this effect that's happening at retirement, I obviously can't change when people retire, but what we'd love to do next time we collect the data is have a new variable, which is the retirement variable. And then all this complexity in the graph that's happening in the mid to upper 60s, all of that will move over to a new 57th graph. That'll be the retirement effect. And then we'll see a cleaner response of risk as a function of intrinsic age with the retirement effect now removed from it. So that's a kind of interesting thing. We're talking about increasing the complexity of the model by adding a feature to it, by adding another graph to it. And yet that could make each of the graphs that we have to look at easier to understand and intrinsically more pure. So that's an interesting trade-off there. Suppose we're an insurance company and we just want to make predictions. We don't want to intervene in anyone's care. It turns out the model's already a good model. We don't necessarily have to fix these things. And in fact, we might be interested in the fact that people over 100 actually have a better chance of surviving from pneumonia, presumably because they get such high quality care. So as an insurance company, we're already happy with the original model. It's telling us about the statistics of the way the world really works. And we're not planning to intervene in that world. So we're happy to use this model as it is. That's a really important lesson that as data scientists, as detectives, we have to take to heart, which is that model correctness, data correctness, the appropriateness of using the model and its predictions completely depends on what we're going to do with those predictions. If we're going to intervene in patient care, then we may have to correct some things in the model. But if we're just going to use the model to make predictions about financial decisions, how much money to keep in the bank, then maybe we don't want to edit the model. This is the most important lesson from the work, is that if you don't know exactly how the predictions will be used, you actually cannot assess whether the model is good or bad, or whether you should edit the model. Let me show you a few things the model learned. It learned that jumps at round, there's jumps at round numbers all over the place in all of the graphs. I can't show you most of the graphs. They're almost always due to sort of human effects, policy effects, social decisions. Very rarely are there phase changes in biology and physics. So these are almost always because of humans. And I'll show you a few more of these on some other graphs for other problems. The model learns, by the way, that asthma is good for you. And it learns that heart disease and chest pain are good for you, that if you've got pneumonia, it's actually good to be not only over 100, but it's good to have asthma, heart disease, and chest pain. Let me show you what the graphs for that look like. So remember, if risk goes down, that means it's good for you. It lowers your risk. So for the asthma graph, if you don't have asthma on the left, your risk is near 0. It doesn't increase your risk very much. But if you do have asthma, it lowers your risk by about 0.2, which is significant. For chest pain, it also lowers your risk a little more than 0.2 if you've got chest pain. And then the biggest effect, it turns out, is if you've got an obstructed airway, which doesn't sound good. But it turns out if you have an obstructed airway, your breathing sounds terrible. And because of that, you'll pay a lot of attention, and your doctors will pay a lot of attention. So it turns out all of these things, asthma, heart disease, and obstructed airway, they're all things that cause you to get to care faster. And when you get to care, to get exceptionally high quality care because you're considered to be seriously ill in a way that it could actually put you at higher risk from pneumonia. So that's what's happening, is the model is learning these confounding effects where these variables, which doctors clearly tell us these are actually bad things for pneumonia patients, these things actually look like, statistically, they're good for you. And that's because these kinds of patients actually got to care faster, and then they got very high quality care when they got there. Okay, so that's a fundamental problem. As a data scientist, these are the kinds of things you need to be able to see in your model so that you can detect these sorts of mistakes that your models are going to make and then fix them. And with this class of model, you can fix these things as well. There's no way to collect a data set that doesn't have these things in it because healthcare is operating for all of the individuals. We're never going to sort of withhold proper healthcare from these individuals just to sort of train a more accurate model. So you have to learn to live with these kinds of things. So just to jump forward, I want to point out that the model is rewarded by predicting all these strange things with extra low accuracy on the test set. And that's because the test set looks just like the training set. It has all the same biases in it. So if we edit the model to correct these effects, the accuracy on the test set will go down. What we believe the accuracy of the model in the real world will go up. So this highlights the large difference we can see between laboratory sort of practice and test sets, which we use all the time in machine learning to evaluate things, and the performance that model might exhibit when deployed in the real world, and how they can be very, very, very different. If you see a model that looks like it has superhuman performance, you really should question whether that superhuman performance would translate to deployment in the real world. Okay, any sufficiently complex model that's accurate is going to learn these things. So it's not just a particular property of this model class. In this model class, though, you can see it and fix these things. You might think you could fix these problems by removing some of these features. Unfortunately, you can't. Because of correlation, the model will learn these same things from other correlated input features. The bias is actually coming from the output signals, not the inputs. All right, let me show you a few things, and then we'll wrap up. So obviously, poor tools make it hard to see things. So this is just a thought experiment. Imagine we have a data set generated by these 3 graphs. So we just have 3 features. And imagine we fit it with a straight line. So that's my example of a poor tool. It's a linear model on data that's obviously not linear. So we might fit a straight line to the first feature that way, to data from the first feature that way, data from the second feature this way, the third feature that way. Those are pretty good fits, right? It's the best you could probably do with a straight line. Here's the interesting thing. If the features are correlated, and if there's any noise in the data, it turns out you may not learn those 3 straight lines. And in fact, it's very possible that you'll learn those 3 straight lines. And notice that the effect for feature 3 actually has the wrong slope. And we see this all the time. This is one of the important reasons for using a model that has sufficient complexity that it can accurately capture the phenomena that's happening in the data. If you use a model that's too simple, it turns out what it's telling you about what it learned can actually be wrong, and signs can even be wrong. So this is very important. Okay, but good tools really do solve some of these problems. So let me just show you some fun things in graphs. So here's a graph of risk as a function of blood urea and nitrogen. And what doctors have told us is so fascinating about this graph is that risk is very high already at 40, whereas doctors tell us they've all been taught that 50, a very round number, is the threshold at which they should start treating patients. So doctors said this was interesting because it told them they should probably start treating patients at a lower level of BUN than they had been taught in med school. But there's something even more interesting happening here. Notice that risk flattens off after 50, and then notice it flattens off and even drops after 100, right? And 50 and 100 are very round numbers. Those are treatment effects. So what's happening is the patients, once they get to 50, are given a treatment. The treatment's very effective, and it actually causes their risk to level off. And once they get above 100, they give an even higher dose of the treatment. And that even in some cases causes the risk to drop. And you end up with weird cases where patients who have BUNs of 90 are actually at higher risk than patients who have BUNs of 110. And that's because the patients at 90 didn't receive as strong a dose as the patients received at 110. So that's sort of interesting. Now here's a question. If we know there's treatment effects in the model like this, should we or should we not edit the model to correct for those treatment effects? Turns out sometimes you should and sometimes you shouldn't. And that's what I'm going to leave you with is imagine the following. Blood pressure is something that's very easy to measure. First thing you do when you get to any doctor's office is they measure blood pressure. You might even be measuring it at home. If we predict that you're low or high risk, the odds are you're still going to get your blood pressure checked. And if the doctor notes that you have very high blood pressure, you're going to receive treatment for it, independent of whether we predicted you're high risk or low risk. So that means if we're seeing an effect, a treatment effect, due to blood pressure in our graphs, maybe we don't have to correct for it, because the intervention that we might do with our prediction isn't going to affect whether you get that treatment. But suppose it's like this. We're only going to measure your BUN, perhaps, if we predict that you're high enough risk that you need the lab test. That means we won't know that your BUN is high if we didn't do the test. So that means our prediction can affect whether you get the test. Therefore, it will affect whether we know your BUN is high. Therefore, it will affect whether you get treated for your high BUN or whether you even get an extra high dose for your high BUN. That means maybe if the model is going to be used in such a way that its predictions could even intervene in whether the test is ever done so that we know you have BUN high enough that you need to receive a treatment, then probably we should correct the model so that it does not predict that you're low risk because you receive the treatment, because then that would be circular. We would predict that patients who did receive the treatment are low risk, then they wouldn't get the test because they're predicted to be low risk, then we would never know they had high BUN and they would never get it, and then they would be at higher risk. Okay, I'm just going to stop there. There's a number of things like this where by having good tools, we're able to find all sorts of defects that happen in the data and that translate to defects in our model. And if we have good tools, intelligibility, transparency into our model, we're able to find these effects, and then we can do what's going to be, in some cases, hard detective work to understand why the model learned that, why that's true in the statistics, and then possibly even harder work to try to decide where should we be listening to a human expert to rewrite part of the model, or where should we trust the statistics that the model has learned and let them stand intact. So this is going to sort of create a necessary kind of dialogue between experts and data scientists and the model to try to figure out what parts of the model should remain unchanged, hopefully most of it, and what other parts of the model actually do need to be edited because of the way the model is going to be used. And you might need to edit a model in different ways for different intended uses of exactly the same model. Thank you. Thank you.